Hearty welcome to today's episode of our online problem solving session series for JAM, NET and GATE aspirants. Today is our 18th session, and in the year 2021, in this new year, this is the first session. I take this opportunity to wish you all a very happy and prosperous new year ahead to all the participants. Let us hope that this year will be really fruitful with lots of mathematical explorations and discussions. Today we have Mr. Arun Kumar CS is with us to discuss some problems in group theory. He is now pursuing PhD in mathematics at Kerala School of Mathematics, Calicut. He completed his MSc from CUSAT, Cochin University of Science and Technology, and also did MPhil. And he cleared many PhD fellowship exams like CSIR, JRF, NBHM PhD fellowship, Case Tech PhD fellowship, etc. I would like to express my sincere thanks to him for accepting our invitation and joining with us. I hope that today's session will be really fruitful to all the participants. And as we know, group theory is one of the important topic for almost all the competitive exams like JAM, NET and GATE. So I hope that today's session will be really helpful for the participants to score good marks in competitive exams and also to understand the concepts in a clear manner. Once again, I welcome all of you to this program. And now I invite Arun Kumar to handle today's session.
We are going to discuss some problems in group theory. Mainly we focus on quotient groups. Okay. So G always denotes group and H denotes a subgroup of G. So recall the definition of quotient group. So for that, we start with some G belongs to G and consider the set GH denoted by defined by G into H, H belongs to H. Okay. Now we denote G by H to be the set of all GH, G belongs to G. Now the question is, can we put a group structure on G by H? Can we make G by H as a group? So the answer is not always. So, but if H is a normal subgroup, that is GH G inverse equal to H for all G belongs to G, then we can make G by H as a group with the following operation. I'll quickly go through this basics for 5 minutes. So the operation is defined like this: G1H, you take two elements G1H and G2H, and the multiplication is defined by G1H, G1 G2 into H. Okay, so this is well defined, only one H is normal. There we using the normality of H, and the identity of H is actually EH, that is same as H, and the inverse, so you take some element GH from G by H, then the inverse of GH is actually G inverse into H. Okay, so suppose you have a group G and H is a subgroup, then you can make G by H as a group provided H is a normal subgroup. Okay, now let's do a simple problem. Let G to be the group Z6. I hope everyone is familiar with Z6, and H to be the group 0, 2 and 4. So H is a subgroup of G. So then compute the group G by H. Okay. So let's do it directly. Like, so you compute the operation is addition modulo 6. So you compute 0 plus H. It will be nothing but, by definition, it is 0 plus H. H belongs to H. So it is 0, 2 and 4. And 1 plus H, this will be 1 plus, yeah, 1 plus H. H belongs to the set 0, 2 and 4. That means this will be 1, 3 and 5. Now suppose you compute 2 plus H, then this will be 0 plus H, and 3 plus H will be equal to 1 plus H, that you can do directly. Something, and 4 plus H will be also same as 0 plus H, and 5 plus H will be also same as 1 plus H. So the group G by H will be, actually it will be 0 plus H and 1 plus H. Okay. Yeah. So one thing you can note here, that the cardinality of G plus H will be, here it is 2, and 2 is actually this 6 by 3, that is cardinality of G by cardinality of H. Okay. So that's also true in general, that cardinality of G by H is same as cardinality of G by cardinality of H. Okay. So yeah. So the purpose of going to quotient group is mainly, so you have a group G, so you can ask, and you have the notion of quotient group, so you can ask, why do you need quotient groups? Okay, so this, or quotient groups, they are otherwise called factor groups. So the idea is basically, so the answer is basically to simplify your problem. Like, your group G can be very complicated, but whereas if you go to G by some modulo some subgroup H, that is G by H, then at least you already seen that the cardinality of the group G by H is smaller than cardinality of G. So your so that while comparing to G by H is simpler. Okay, that's why we look into the quotients in general, wherever in mathematics, like if you go to vector spaces, like you have the notion of quotient vector spaces, quotient rings, everything is there. Like this purpose is basically to reduce your problem. Okay, yeah. So we'll do some problem from JAM 2015. Okay, so which are the following? Statements are true. So the first statement is basically a factor group. Quotient groups are otherwise called factor groups. The factor group of an abelian group is abelian. A factor group of a cyclic group is cyclic. A factor group of a non-abelian group is non-abelian. A factor group of a non-abelian group can be cyclic. Okay, so let's do the problem. So the first statement says that a factor group of an abelian group is abelian, right? So we start with an abelian group G. Let G be an abelian group, and you take any subgroup H. Let H be any subgroup. Then H will be
Hello, Arun. You can ask for participants to react. Somebody
So
answering in the chat.
Yeah, sure, sir. Yeah, is that fine? I am audible and are you able to see me? I like see the question clearly, right?
Yes, clearly.
Okay?
Yes.
Everything fine, right?
Yeah.
Okay. Yeah. Yeah. So, like, if somebody have some comments, you can like put it in the message box.
Yeah, participants, you can answer the question in chat box, or if you have any comments, you can make it in the chat box. Okay.
Yeah, somebody's written like A, B, and D. Like, sir. So it will be helpful if we can read the answers in the text box. If
you cannot be you are not able to see the chat box during presentation. Okay.
Yeah, correct.
Okay. So I will inform you. Okay.
Yeah, that will be better. Thank you, sir. Yeah. So you start with the group G, abelian group G, and H be a subgroup. So in the case of abelian group, all subgroups are normal. All subgroups are normal because you have this commutativity relation. G inverse will be obviously. So by definition, this is G inverse, H belongs to H, but G is commutative, so this will be H. So therefore, H is a normal subgroup. So you can take G by H. You can consider you consider G by H, then it will be a group. It will be the quotient group, and so you take two elements from the group. Let's say G1H and G2H. Then G1H into G2H is by definition this is G1 G2H, and by commutativity of G this is G2 G1H, this is equal to G2H into G1H. So G by H is abelian. Okay, so statement A is true. Now you look at the statement B. A factor group of a cyclic group is cyclic, right? So you start with a cyclic group. Let's G be a cyclic group with generator G. That is G is generated by G, small g, and that is this is equal to G raised to n belongs to n, right? Then you can easily show that again this G is cyclic, so G is abelian, so any subgroup H will be normal. So you, for any subgroup you have G by H will be a group. So so for any subgroup H, this GH, the same GH will generate so GH will be G by H will be generated by G into small h. Okay, so the statement B is also true. Now the third statement is a factor group of a non-abelian group is non-abelian. So you have a factor group, you have a non-abelian group G, and the question is whether for all subgroups normal subgroup H, G by H is non-abelian. So if you consider the example, take the example G is equal to, let's say, S3. This is non-abelian. So first non-abelian group.
So that example is given by one student in Bishajit Ganguly in chat box.
Wow.
See,
Okay.
Arun, if you have a mobile phone with you, you can join through that also. That
Yeah,
then
yeah.
you can get both comments as well as this.
Oh, that will be useful, right? Okay. Yeah, yeah, sure, sir, sure, sir. Just 1 second, 2 seconds, huh?
Okay.
2 minutes.
Okay, no problem.
Yeah. Sir? Yeah.
Okay. Yes. You keep the audio in the other one muted.
Oh. Which one? Mobile or
Yeah.
the
You can keep one you need as on, the other one off.
Is that fine now?
Yes. Okay.
Hello?
Okay. Now it's everything okay.
Okay. Yeah, okay, sir. So, but no, I joined now only, so I can't see the earlier message.
Okay. No problem.
Yeah. Okay, from next. Yeah.
Yeah.
Yeah, okay.
Biswajit Ganguly was given the
Yeah, fine. So
example.
anyway, I'll explain
Okay.
like
One participant given as an example as the group as S3 and N as A3, so that G by N will be isomorphic to Z2, which will be cyclic.
yeah, correct. Yeah, it's a group of order 2 and it will be isomorphic to Z2. Yeah, correct. Okay, sir. So C is not true, but D is true. The same example will work for D also. Okay. So go to next question. So this is asked for JAM 2018. Let G be the quotient group. Q by Z. Q is a set of rational numbers and Z is a set of integers. Which of the following statements are true? So the first statement is basically every cyclic subgroup of G is finite. Second one, every finite cyclic group is isomorphic to a subgroup of G. So how the quotient group Q by rational numbers mod integers. Okay. So in that group Q by Z, the question is whether every cyclic subgroup of G is finite. And the second statement is basically every finite cyclic group is isomorphic to a subgroup of G. So anybody have any comments or any idea? So anyway, let's try to do this problem. So let H be a cyclic subgroup
Somebody commented
of
some answer.
G. Yeah, he said both true. Yeah. Okay, let's see how to do this. So our group is actually Q modulo Z, right? So uh, so the elements of Q modulo Z will look like some rational number P by Q plus Z, right? P belongs to Z, Q belongs to N, and right? Okay. So so you take some element p by q, one element p by q plus z from q by z. Then can you tell me what is the order of this element in q by z? What is the order of p by q plus z in q by z?
Arun, the answers are coming in chat box.
Yeah, yeah, yeah. So it's exactly correct. They said it is q. Yeah. So order of this will be q, because q into p by q plus z is basically how do you multiply this? This is actually q into p by q plus z. This is equal to p plus z. Since p is in z, so p plus z will be equal to z, and z is the identity element. So for the order of p by q plus z is q basically. So now you have a cyclic group, so h that will be generated by
Uh,
some element
uh,
p by q plus
uh,
z.
Arun, someone has a
Okay.
comment in chat box. You just look
Yeah,
at.
yeah, correct. Thank you. That is correct. So this GCD of P and Q is 1. Yeah, correct. Yeah. So in the definition of Q by Z, I put GCD of its elements are of the form P by Q plus Z with the GCD of P and Q is 1. Yeah. So yeah. So now you have a subgroup H, cyclic subgroup H. So that is generated by some element P by Q plus Z. Then then cardinality of H is same as order of p by q plus z. This is same as q. So this is finite. So the statement 1 is true. Every finite every cycling subgroup of G is finite. Okay. So now you look at the statement 2. So it says that every finite cyclic group is isomorphic to a subgroup of G. So how do you do that? Statement 2. So you start with a finite cyclic subgroup. Let H be a finite cyclic subgroup of G. Sorry, not subgroup. You take arbitrary finite cyclic group. Now, suppose the statement is true, then what you have to prove? Then you have to find a subgroup of cyclic subgroup of order H in Q by Z. Okay. So yeah. So it is. So let uh, order of H is equal to n. Then can you construct an element of order n? Can you construct an element of order n in Q by Z? Anybody? Yeah, few answers are there. So again, Vishwajit Ganguly and Diya Saha. Yeah. So they said consider the element 1 by n plus z. Yeah, exactly. So take 1 by n plus z belongs to q by z. Then order of 1 by n plus z will be what? This will be n because n into 1 by n plus z is basically 1 plus z is same as the identity element z. Okay. So let H1 to be the subgroup generated by 1 by n plus z in q by z. Then H1 is a cyclic group of order n and implies H1 is isomorphic to H. So the statement 2 is true. Yeah. So this group U by Z is a very interesting one. So I'll tell you one another property. So maybe I will put it as a question. So does there exist an infinite group in which every element has finite order? So the question is, does there exist an infinite group in which every element has finite order? So I already told you. So we are discussing about the group Q by Z. So maybe you can check in Q by Z. So for the first, is Q by Z is an infinite group? So how do you say that Q by Z is an infinite group? So you again, like earlier, you take 1 by n plus z. You consider the set 1 by n plus z. N belongs to n. This is a subset of Q by Z, and it's basically infinite because, so to say this is an infinite set, it is enough to say 1 by n plus z is not equal to 1 by m plus z when m not equal to n. So this directly follows because these are equal if and only if, since 1 by n plus z equal to 1 by m plus z, if and only if 1 by n minus 1 by m belongs to z, but this is not true. True. The last line 1 by n minus 1 by m belongs to z is not true when n not equal to m. So this is an infinite subset of the group Q by z. So it's an, let's say it's an infinite, it's an infinite group. Okay. So yeah, now we already shown that an element of Q by Z is of the form P by Q plus Z, and its order is Q. So every element has finite order, right? And we already seen the order of P by Q plus Z is Q, which is finite. So Q by Z is an infinite group in which every element has finite order. Maybe I can give you another interesting example. So like you start with a set X, let X be an infinite set, and P of X be the power set of X. Okay. Can anybody make P of X as a group? Can you think of a group structure on P of X? P of X is basically the power set of X. It's basically a collection of subsets. Yeah, somebody answered. Yes, with symmetric difference. Yeah. So it's very good. So you consider the relation symmetric difference. Maybe you can check whether the usual set union or intersection makes P of X as a group, and that is not the case. But if you take the symmetric difference, consider the symmetric difference. Delta, so let me denote it by delta of AB for two sets A and B. This is A difference B union B difference A. So then P of X, or maybe I'll denote by A star B. A star B I'll define by symmetric difference of A and B. Then P of X with a star is a group. So what will be the identity of this group? So you can easily show that identity of this group is the empty set, and what will be the inverse of A? What will be the inverse of A? You take A subset of X, or A belongs to P of X, then what will be the inverse? So you see A star B equal to B, yeah, empty equal to B star A, right? So this means A difference B union B difference A has to be empty, right? So union of two sets is empty, so each one has to be empty. So this implies what? B has to be equal to A. So that is, yeah, the inverse of A is basically A itself. So that means what? In this group is equal to, let's say, identity, right? Correct? What is the asymmetric difference? A is empty set. So that means in this group, the order of A is 2 in this group. So this is an interesting example. So you have power set and you are making power set as a group, where that is a property that all elements, its inverse are itself, right? Self inverse. A is the inverse of A itself, and that means its order of A is 2 for every subset. So maybe you can, so maybe if one you can take another groups, you take 2 raised to n nth root of unities. This will be also a infinite group where each element has finite order. Maybe one more example I can quickly give. You take Z2 cross Z2 cross etc. This will be another example, and you can nothing to do with 2. You can take any n, and you can find group infinite group where each element has finite order. Okay, fine. Now we'll go to the next question. So you have two groups G1 and G2, and H1 and H2 are subgroups which are normal in GI. So let's say HI is normal subgroup of GI, I equal to 1 2. That means G1 and G2 are groups and H1 and H2 are normal subgroups. Okay, so assume that G1 by H1 is isomorphic to G2 by H2. Okay, and which are the following? Statements are true. So the first statement is G1 and G2 are isomorphic. H1 and H2 are isomorphic. See, if H1 and H2 are isomorphic, then G1 and G2 are isomorphic. And so the next option is meaningless. This is like none of the above. Yeah, so for a completion I will write that. Okay. Yeah, so you have two groups G1 and G2 and subgroups H1 and H2 such that G1 by H1 is isomorphic to G2 by H2, where G1, H1 and H2 are normal subgroups. So the question is whether G1 and G2 are isomorphic. Second question, H1 and H2 are isomorphic. If H1 and H2 are isomorphic, then G1 G2 are isomorphic, and all the statement can be wrong. So anybody have any comment or any answer? So, hello? Yeah.
Yes, some answers are coming in the chat box.
Yeah, I'm seeing that. So many people saying C is so like yeah. So let's try the first option. So the question is basically you are given G1 by H1 and G2 by H2 are isomorphic, right? So Yeah, maybe I'll give the example. So you take that statement may not be true. So you take you can consider simple example. Let's say G1 to be, let's say, Z4, and H1 to be the subgroup generated by 0 and 2. Then G1 by H1 will be what? It will be a group of order 2, so it will be isomorphic to Z2, right? And if you take G2 to be, let's say, ZA, or if one you can take Z6, and H2 to be the group 0, to be the subgroup 0, 2, 4 and 6. Again G2 by H2 is a group of order 2. Yeah, essentially we are using that this, given that G1 by H1 is isomorphic to G2 by H2, so their cardinalities are same. So we are considering a particular cardinality, a number, let's say here it is 2, in which there is only one group up to isomorphism. That means you can take any prime number, and if you take two groups G1 and G2, with the G1 by H1 has cardinality P and G2 by H2 has cardinality P, then the quotient groups will be isomorphic, and you can make G1 and G2 need not be isomorphic. So G2 by H2 is a group of order 2 and hence isomorphic to Z2. So therefore G1 by H1 is isomorphic to G2 by H2, but what? But G1 is not isomorphic to G2 because these cardinalities are not same. Like G1 have cardinality 4 and G2 have cardinality 8, and of course H1, again the same reason, H1 is not isomorphic to H2. Therefore the statements A and B are false. Okay, so what about C? Many people are saying this C is true. Yeah, again one guy answered for C. No, that's for A and B. Then we are false by taking G1 equal to S3, H1 equal to A3, etc. Yeah. So for C also you take the same example that Vishwajit Ganguly given. So you take G1 to be S3 and H1 to be A3. Then again G1 by H1 is a group of order 2. This is basically 6 by 3. So G1 by H1 is isomorphic to Z2, and take G2 to be Z6 and H2 to be Z3. Again G2 by H2 is a group of order 2, so it is isomorphic to Z2. Therefore G1 by H1 is isomorphic to G2 by H2, but S3 is not isomorphic to Z6. For example, this is Z6 is cyclic or abelian, X3 is not abelian or cyclic. So yeah, also this H1 and A3 is actually a group of order 3, and group of order prime is cyclic, so A3 is, and cyclic group of same order are isomorphic, so A3 is isomorphic to Z3. So H1 and H2 are isomorphic and the quotient groups are isomorphic, but the original groups that you started with are not isomorphic. Yes.
এখানে G2 equals to Z6 and H2 equals to Z3. Is Z3 is a subgroup of Z6?
I know, yeah. So that means what I mean is you take the subgroup which is isomorphic to Z3. There is a subgroup of order 3 that's basically 0, 2, and 4. Thank you. Yeah. Okay. Okay for you? Is that fine? Yeah. Yeah. So of course, somebody has asked a very good question. If G1 and G2 are isomorphic, then is that the case H1 and H2 are isomorphic? Yeah. So the question is basically if G1 by H1 is isomorphic to G2 by H2 and G1 is isomorphic to G2, then H1 is isomorphic to H2. That is a question he posed. It's a very good question. So, so the answer is basically uh, H1 is isomorphic to H2 if and only if H1 and H2 are conjugates. So for the time being, I don't want to go to the details of proof. That proof is not that much easy, but to do a lot of computations. So just keep the statement H1 and H2 are isomorphic if and only if H1 and H2 are conjugates. That means uh, there exists some G such that H1 equal to GH G inverse. Okay, fine. Yeah. Anyway, it's a nice question. That yeah, very good. Yeah. Now we'll move to the next question. So it's a question asked in JAM 2009. So it's the lengthy one. So maybe I'll. So G is a group, and A of G denotes the automorphisms of G. That means set of all phi from G to G, phi is an group isomorphism. Okay, and this I of G is a special automorphism. Phi A belongs to G, where phi A of G is A inverse GA. Conjugation automorphism is called inner automorphism. These are called basically inner automorphisms. Okay, so the first question is basically, so you can easily check that A of G is a group and H of I of G is a subgroup, and the question is show that I of G is a normal subgroup, and second question, show that I of G is isomorphic to G by center of G. Center of G is actually all those elements G belongs to G such as Gx equal to Xg for all X belongs to G. Set of all elements that commutes with all other elements of the group. And third question is find automorphism of, let's say, of the group Q. Okay. So A of G denotes all automorphisms, I of G denotes inner automorphisms, and the question is to show I of G, show that I of G is a normal subgroup. Okay. So you take So to prove I of G is a normal subgroup, you have to prove phi inverse belongs to I of G for all phi belongs to A of G. So you start with phi belongs to A of G, and what phi A belongs to I of G, and I have to prove phi A phi inverse belongs to I of G, right? So now you compute what is phi A phi inverse. So yeah, so phi A phi inverse of X. So this is basically yeah. How do you show that this is a normal subgroup? So this is by definition. This is basically phi of A inverse. This is basically okay. So maybe I'll phi A of phi inverse of X. So phi inverse of X is basically so what will be phi inverse of X? It will be phi of X inverse, right? So this is A inverse A, and phi of A inverse phi of if one let's just keep it as phi inverse X. That's enough. Phi inverse. So this is phi inverse of X phi of A, and this is basically phi A inverse X phi of A. So this is phi of, by definition of conjugation, this is phi of A of X. So this phi A phi inverse belongs to I of G for all phi belongs to A of G. Therefore I of G is a normal subgroup, okay, of A of G. Fine. Is that okay for you? Yeah. So the part B says that to show I of G is isomorphic to G by center of G. I hope you are familiar with center of G. Center of G is a set of all elements commutes with all other elements of G, and so we want to define a map from I of G to G by Z of G. There are many ways to do that. So here I will do, you take some, you want to define a map F from, let's say F from I of G to G by center of G. So you take some phi A, take some element of I of G, it is phi A, then you want to define F of phi of A. So you have an element A belongs to G. So naturally what you do, you define it as A into the coset of the equivalent class of A mod Z of G. Okay. So you define f of I of a to be a into z of g. So then show that f is well defined and f is a bijective group homomorphism, or in fact it is an isomorphism. Yeah. So this well defined part and the injective part, one part can be done simultaneously. So you let's say assume phi of, let phi for suffix a equal to phi suffix b, a comma b belongs to g. Then you have to show f of phi of a equal to f of phi of b. So this means that, so a inverse, you apply the definition of phi and phi b, implies that a inverse x a equal to b inverse x a x b. So that means you pull out this b to the left side, so this will give you b a inverse x a b inverse equal to x. So that means a b inverse or inverse x a b inverse equal to x. So implies that this is nothing but phi suffix a b inverse of x equal to x, that is phi of a b inverse is the identity map. So what? So yeah, so actually sorry, this is not required. Like from here, this is not required actually, I'm sorry. So this implies that b a inverse x equal to x. Yeah, so it's okay, it's a little bit messy. So that means b a inverse, actually I want to say that b a inverse commutes with all other elements of g. So that is that means b a inverse commutes with all elements of g. That means b a inverse belongs to center of g. So now you know that two cosets are equal if and only if this condition b a inverse belongs to the group, right? So this means that a z of g equal to b z of g, implies that this is what our definition of f of phi of a, this is f of phi of b. So this is well defined. So now you go to the uh, reverse direction, you can show that this is injective. So therefore f is well defined and injective. Yeah, sir. Hello. Hello.
Yes.
Yeah. Now, yeah. So now one interesting problem. See, find the automorphism of the group Q. Yeah. Now you can. So I forgot to tell you. You can directly show that it's a homomorphism, and it's by definition itself it is onto. So that completes the proof. And now the question is, find the automorphism of Q. Okay. So yeah. So to find this, so look at, let's say phi of 2. I can write 2. So okay. Let phi be an automorphism of Q. group isomorphism. Okay, then then so you analyze the value of phi at 2. I can write 2 as 1 plus 1. So this is by this should be, hello, somebody is
Hello.
saying something.
Okay.
Sir, are you saying something?
Nothing. I think somebody has kept on
Hello?
mic. Okay. Okay. Now it is clear.
Yeah, please tell them to mute the audio.
Okay.
Yeah.
Okay.
So yeah. So phi is a group isomorphism. This will be phi of 1 plus phi of 1. So this is 2 times phi of 1. So therefore, similarly, you can say phi of n is equal to n. You can write as 1 plus etc. plus 1. So this is same argument as earlier. This is n times phi of 1. So that means yeah. Okay, so that is there. Now you compute, see this, you can write phi of 1 as phi of 1 by n plus 1 by n plus etc. 1 by n. Yeah, essentially I am writing 1 as n by n. So n by n I am writing as n times 1 by n, right? So this is n times phi of 1 by n. So that implies phi of 1 by n is actually 1 by n times phi of 1, right? Correct? So similarly, again, what will be phi of p by q? This I can write it as phi of 1 by q plus 1 by q plus etc. 1 by q 3 times. So this is nothing but 3 times phi of 1 by q. So we already seen phi of 1 by q is 1 by q times phi of 1, right? So this is actually p by q times phi of 1, right? Therefore, so you see that, so all rational numbers are of the form p by q, and phi of p by q is actually p by 2 times phi of 1. So it's, the value of phi is completely determined by its value at the number 1. So phi of x is actually x into phi of 1 for all x belongs to q. So yeah, so if suppose I denote c by phi of 1, so phi of phi is actually, or phi of x is actually c times x. Therefore all automorphisms of q are of the form automorphism of q is of the form, let me denote this map by phi c. C belongs to, yeah, c belongs to q. I'll say q minus 0 because we want it to be an isomorphism. So suppose I take c to be 0, phi is identically 0. That's a trivial case. We'll exclude that. Yeah. So that's automorphisms of q, right? And maybe if one, you can identify this with the q star, with the multiplication. Okay. Yeah. Sir, is there any questions up to this point? Hello, sir, are you able to hear me?
Yes. No problem.
Is the yeah? Can you ask if up to this point is there any question? Like
Okay, participants, if you have any question, you can ask here or you can comment in chat box. Some voice is coming. I don't know. See, some comments are there in the chat
Yeah,
box.
okay. Okay. Oh, they're saying one person is asking, can you repeat A and B once again? Okay. So somebody saying what is an automorphism and inner automorphism with some examples. Yeah. Yeah. So part C already explains what's with an example. We classify all automorphisms of Q that you can see.
Okay, no need to repeat the thing because we
Yeah,
will
yeah.
upload the
Yeah,
material.
yeah, that is fine. Yeah. Okay. Then I will move to the next question. Yeah, so this was asked for NBHM, MSc 2016.
Some noise is coming. I don't know from where, but I'm not seeing anyone.
Oh, maybe I don't know. Sir. Yeah. So, so let G is equal to GL2 of R. Yeah. So this is basically set of all 2 by 2 invertible matrices with real entries, which are the following: subgroups are normal, and in each of the cases, where H is a normal subgroup, identify the quotient group. Okay. Yeah. So the group under consideration is the set of all 2 by 2 invertible matrices with real entries. Is a group under usual matrix multiplication, and the usual inverse is basically the inverse of a matrix in this group, and usual identity matrix is the identity of this group. So the first one is H1 is a subgroup SL2 of R. This is basically set of all A belongs to GL2 of R, set of all 2 by 2 invertible matrices with the determinant 1. Okay. Second option, H2, set of all upper triangular matrices, matrices, sorry, in GL2R. H3, set of all diagonal matrices in GL2R. D, H4, set of all matrices with positive determinant. Okay. Yeah. So the first option is basically SL2R matrices with the 2 by 2 matrix invertible matrices with the determinant 1. Is that a normal subgroup? That
বি
is the
নাম্বার
question.
অপশনটা কি বললেন লিখেছেন স্যার?
Yeah. So this is basically a group because if A and B are in this SL2R, then determinant of A into B is basically determinant of A into determinant of B. Yeah.
I think somebody asked a question.
I
Shubham
couldn't
Kundu.
hear you. Yeah, I
Can
couldn't hear you.
you repeat, Shubham, your question now?
স্যার অপশন ডি মানে কি বলছে, মানে কোশ্চেনটা কি স্যার? অপশন ডিটা অপশনটা কি? হোয়াট ইজ দ্য স্যার অপশন ডি?
Yeah, set of all matrices with a positive determinant. 2 by 2 matrices. Yeah, set of all 2 by 2 matrices with a positive determinant. Okay. Yeah. So this is SL2R is basically a group because if A comma B belongs to SL2R, then determinant of A into B is basically determinant of A into determinant of B. So this both are 1, so this is 1, so that is fine. In fact, determinant of A into B inverse will also have determinant 1, so it's a group. So the question is basically it's a normal subgroup. So you take some A belongs to GL2R and B belongs to B belongs to SL2R, then A inverse BA, whether A inverse BA belongs to SL2R. That is the question. This has determinant 1 or not. That's the question. So you compute the determinant. So this will be determinant of A inverse into determinant of B into determinant of C, determinant of A. This is equal to 1 by determinant of A. Determinant of A inverse is 1 by determinant of A, and this is determinant of B into determinant of A. So that's equal to determinant of B. This is equal to 1 as B belongs to SL2R. Therefore, A inverse BA belongs to SL2R. This is one proof. Yeah, if want I can give you another proof. Like let's say, I hope you are familiar that kernel of a group homomorphism is a normal subgroup. So we define a group homomorphism phi from GL2R GL2R to, let's say, R star R minus 0 with multiplication phi of A is nothing but determinant of A. Then phi of A into B is basically determinant of A into B, so determinant is basically multiplicative. So that means this means that actually determinant is a group homomorphism in this group. On the group, okay. Therefore, phi is a homomorphism, and what will be kernel of phi? This will be set of all A belongs to GL2R such that determinant of A equal to 1. This is nothing but SL2R. So,
sir, a question.
yeah, okay.
So it's a date A inverse equals to 1 by date A. This is always right.
Yeah, for invertible matrices it is true. You see, yeah. So I will give you a quick proof. That's very easy. You can also see. You use this relation A inverse is I, right? So
Yes,
you
yes.
apply determinant here. So determinant of A inverse will be determinant of I, that is 1. So this
1.
is determinant is multiplicative. So this is 1. So right.
Oh, only invertible matrix.
Yeah, yeah. We are in a group where we are in GL2R, where all the matrices are by assumption it is invertible. That's the notation GL2R. We
Oh,
consider all invertible 2 by 2 real matrices.
oh, okay, okay,
Okay.
okay, okay.
Yeah. Okay. So this kernel of phi is actually kernel of determinant is basically SL2R. So that's why this is a normal subgroup. In that way also you can say this is a normal subgroup. So yeah, now the question is, so this is a normal subgroup, so we need to find what is G by H, right? That is SL2 GL2R by SL2R, right? So here we will use this the last argument. So we have phi from GL2R to SL2R. Phi of A is equal to determinant of A. It's a group homomorphism with the kernel SL2R. Sorry, the isomorphism group homomorphism is to R minus 0. Yeah. So here we use a very good theorem in group theory, like so isomorphism theorem. So by isomorphism theorem, what you can say, GL GL2R GL2R by SL2R is isomorphic to image of phi. And what will be image of phi? Image of phi will be actually R minus 0, that is uh, phi is onto as you take, let's say, let A belongs to R minus 0, then consider the matrix A0, let's say 0 1. This is invertible, this is determinant non-zero, so it is invertible, and this, and phi of A0 0 1 is determinant of that is basically A. Therefore, it is an onto homomorphism, and so the group GL2R, the quotient group GL2R by SL2R is isomorphic to R minus 0 with the multiplication. Okay. Yeah. So part A is done. Now part B. Part B is a set of all upper triangular matrices of in GL2R. That is H2 is of set of all matrices of the form A, B, 0, C with A into C not equal to 0. Right? A, B, C belongs to R. Yeah. Yeah. So first of all, we need to check whether this is a normal subgroup. So how do you do that? Any guess? Is that a normal subgroup? Yeah, maybe we'll give
Sir, take
what?
A equal, sir, take A equal
Yeah.
হচ্ছে GH
Sorry.
B G মানে যে কোনো আরবিটারি ম্যাট্রিক্স A B C D matrix and H equal হচ্ছে let হচ্ছে GF0C, then H inverse belongs to does not belongs to H.
Yeah. How do you say that?
So because ये 2x2 matrix सर हिंदी तो बोलूंगा सर, मैं हिंदी में बात
Can you speak in English?
सर my English
Yeah,
is
you can
very
tell. Yeah, I can. It's okay. You tell.
sir which মানে sir arbitrarily choose sir, we can choose A equal ABCD, arbitrarily matrix ABCD
So you are
arbitrarily
taking a matrix from GL to R, ABCD.
Take A
ABCD
equal to 2 1 1 1 and B equal to -1 0 0 1. Then compute AB A inverse. We get -3 4 -2 3, which is not upper triangular as well as not diagonal.
Yeah, correct. That's good. Yeah.
Thank you, sir.
Yeah. Okay. Yeah. So what they are saying is you are taking an arbitrary matrix. A belongs to GL to R, and some particular matrix, like some matrix. Okay, maybe I'll give you one precise example. That's better. So you take 1 0 0 2. It's an upper triangle matrices. It's an upper triangle matrix. It's actually belongs to H2, and in fact this belongs to H3 also. It's a diagonal matrix, and if you take A is equal to 1 0 1 1, this belongs to GL to R. Then suppose this is normal, then A inverse B A will belongs to H2. But if you compute A inverse BA, so the inverse of this matrix is basically 0 1 0 minus 1 1 into 1 0 0 2 into 1 0 1 1. So this is basically 1 0 minus 1 2 into 1 0 1 1. This will give you, so to show that this is not upper triangular or diagonal, it is enough to find this entry, right? So this entry will be, you will have some entries here and here, and this entry will be 1. So this does not belongs to H2 or in H3, right? Therefore H2 is not normal. And by the same reasoning, H3 is also not normal. Yeah. What about D? Yeah. What about D? Somebody? What is H4? H4 is actually 2 by 2 not diagonal, sorry.
सर ट्रू होगा सर,
Sorry,
सर D ट्रू.
Sir,
Yeah.
option D is true.
yeah, 2 by 2. Then you find the quotient group. 2 by 2.
So a set হচ্ছে which contains all the positive determinant matrix and H, and other is all the EA matrix which are determinant is negative. These two মানে isomorphic to Z2.
Yeah. So if you take some A belongs to GL to R and B belongs to H4, then A inverse BA determinant of A inverse BA is same as determinant of B. This is positive. So by assumption B belongs to H4. Therefore determinant of A inverse BA is also positive. Implies A inverse BA belongs to H4. Therefore H4 is normal. Yeah. Now the question is, how do you find, how do you identify the group GL2R by H4, or what is the group GL2R by H4? Is isomorphic. How do you find this? So you can guess that you are, in a sense, you are dividing by matrices with the positive determinant. You have only two possibilities: matrices with the positive determinant and matrices with the negative determinant. So we are identifying all matrices with the positive determinant as one class, and so then of course the matrices with the negative determinant will come into the other class, right? There are only two possibilities. So how do you prove that? How do you give a nice proof? So for that, maybe you find a group homomorphism whose kernel is H4 to suitable space. So
Sir,
we define, yeah.
sir, we can map the positive determinants to 0. No, the positive determinants to 1 and the negative determinants to 0. So
Yeah.
we can find that GL2R by H4 is isomorphic to Z2.
Yeah, that's correct. Can you find an explicit expression for that, whatever your map? Your map is exactly correct, I will say. But so I will give you a matrix. How do you let A be a matrix? Then how do you say that? Yeah, can you give an explicit expression for that instead of saying like if A is
If
positive?
determinant A is positive, then we map it to 1.
Yeah, correct. So
And
you
if
want, yeah, correct. Okay.
and if determinant A is negative, then we can map it to 0.
Yeah, what is that
And
function actually? Explicit expression I am saying, asking. Yeah, you are right, absolutely right. But you can find an explicit expression for that, right?
yes,
If some number is positive, it is 1, and if number is negative, it is -1. What is that function? Yeah, okay, I'll give you it. You are right, it's exactly right. So I'll define phi from GL to R to the group -1, 1. So Z2 is basically phi of A is determinant of A by modulus of determinant of A. Right? You consider, look at the function x by mod x. This will map x to 1, right? If x is positive, -1 if x is negative, right?
yes, sir.
Yeah, good, very good. That's what I use. So you said if determinant is positive, it is 1, and if determinant is negative, it is -1, right?
Yes, sir.
So you compose that function with the determinant. So that means phi of A is actually determinant of A by modulus of determinant of A. Okay.
Okay, sir.
Yeah. So this is a group homomorphism, and what will be kernel of phi? Kernel of phi is actually, yeah, kernel of phi is actually set of polar such that determinant of A by mod determinant of A is equal to 1. So this is A such that determinant of determinant of A equal to mod determinant of A. That means what you want, determinant of A has to be positive. X is equal to mod X means X is positive. So this is our H4. And is that an on? So by definition itself, it is an onto homomorphism because the determinant of phi of identity matrix is 1 and phi of minus, no, not minus, phi of identity matrix is 1 and phi of 1 0 0 minus 1 is basically minus 1. Therefore phi is 1. Therefore GL2R by H4 set of all matrices with positive determinant is isomorphic to Z2. Okay. Yeah. Now I'll do one more question. So this was asked for TIFR 2013. So it's a simple question. So does there exist an onto homomorphism? Or in which of the following cases there exists an onto group homomorphism? Which of the following cases there exists an onto homomorphism, group homomorphism? So which one? From S5 to S4, B from S5 to S2, C from S5 to Z5.
Sir, can you
Yeah,
repeat the question, sir?
yeah. In which of the following cases there exists an onto homomorphism? Let's say from S5 to S4. Does there exist an onto homomorphism from S5 to S4, S5 to S2, S5 to Z5? S this S5 is Sn is basically symmetric group on n lattice. So set of all permutations of this n element set. So we are doing problems related to quotient groups. We can, and basically when you take quotient groups, you are considering normal subgroups, so you should be aware of what are the normal subgroups of Sn, and you use that.
Many of them are answering as B.
Yeah,
Chat box.
yeah, I see. Yeah, okay, yeah, that's correct. So, so, so what is the isomorphism from onto isomorphism from S5 to S2? Yeah, B is true. So what is the isomorphism? So, so S2 is actually permutations of two element set. That is, S2 is nothing but Z2. So basically, you define phi from S5 to S2. Um, like phi of some permutation, phi of sigma is equal to, let's say, 1. If 1 is the identity element of S2, sigma is an even permutation, and let's say minus 1 if sigma is an odd permutation. You can say, okay, if I am seeing Z2 as set 2. It's isomorphic set 1 minus 1 with multiplication. Okay, so this is basically the sign of sigma. Okay, that is phi of sigma is the sign of sigma. Sign of a permutation is 1 if it is an even permutation, minus 1 if it is an odd permutation. Like it's defined in terms of the number of transpositions. Okay. So this is a homomorphism. Yeah. Now why there does not exist a homomorphism from S5 to S4? So here we use the fact that the only normal subgroup of S5 only proper.
So suppose there exists a onto homomorphism from S5 to
Yeah.
S4, then
Okay.
then by first isomorphism theorem, S phi by car phi is isomorphic to phi of S5. So
Yeah.
in S5 the kernels are identity or A5 or S5. So in both cases we get a contradiction.
Yeah, that's what I'm also saying. So um, so there you should be careful, or you should aware of that the only proper normal subgroup of S5 is A5. So then if phi from S5 uh, to let's say S4 is an onto homomorphism, then by isomorphism theorem S5 by kernel of phi will be isomorphic to S4, but kernel of phi has either identity or A5 or S5, but it is not 1 so you can cut it off identity, and it is not like the cardinalities are not, it's not injective basically. Yeah, so and it is not, it's a non-zero homomorphism, so you can cut it off S5. So kernel of phi must be A5. Okay, so then S5 by A5 cardinality is, this is actually 2, but S4 cardinality of S4 is 4 factorial, implies S5 by A5 cannot be isomorphic to S4, implies there does not exist an onto homomorphism. Now the same reasoning can be given to part C also, since again S5 by F5 have cardinality 2 and cardinality of Z5 is 5, S5 by F5 cannot be isomorphic to Z5. So there also C is all not.
Hello, sir. Is it audible?
Yeah, you are audible.
Okay, sir. I'm Jasim from Kerala. Now I'm
Oh,
degree
okay.
third year student preparing for JAM. Actually,
From
this
where?
class was very effective because from Kerala.
Yeah,
Which
okay.
college?
In our
Which place?
degree
Which
syllabus,
college?
St. Joseph College, Devri, Calicut.
Oh, I see. Okay. You
Uh,
are very near to me. Yeah. Okay.
okay. Actually, this topic of factor group is not included in our degree syllabus. syllabus.
Oh,
So this class was very effective for our entrance preparation. So
yeah.
I'm very
So if you don't know, like
happy
you
to
should
say
learn
thanks
factor
to
groups.
you
Like
and Vinod sir for
so, all
arranging
the
this class.
things will, all the proofs later rely on the quotient groups. So you should learn that properly. Okay, not for only the entrance. For future your studies in group theory, you should be very aware of this quotient groups.
Okay, okay.
Yeah.
Okay, okay. Then can you um, suggest some tips for TIFR preparation?
Yeah. So there is a like there are two books that you can follow. There's a book by Bernstein, Topics in Algebra, and there is a book by Dummit and Food, Abstract Algebra. Okay, so you just do the exercises in that book. That will be better. Jasim, are you able to hear me? If want, I can repeat. Topics
Okay, sir. Thank you so
Topics
much.
in Algebra by Bernstein
Okay.
and Dummit and Food book Abstract Algebra. Okay, it is available in your
Oh,
library. Yeah, I'm sure.
oh, okay, okay.
Or
Yes,
in your
yes.
department itself. I
Yes, it will be available.
Yeah, and if want, you can come to KSM also. It's very nearby, just 3 kilometers. Yeah,
Yes, yes, yes. Okay, thank you,
yeah,
sir.
sure. Yeah. Okay.
Good afternoon, sir.
Yeah,
Yeah. Hi.
those. Yeah.
Sir, I am Dia from West Bengal. I read in Ashutosh College. Uh, I am preparing for JAM 2021 and also other competitive exams. This session is very beneficial for us, and sir have discussed many previous year questions also. Thank you, sir, a lot.
Yeah, all the best. Thank you.
Thank you, Dia. Thank you.
Yeah,
Yes.
I'm Sri Lakshmi, a third year BSc Maths student from Malabar Christian College, Calicut, Kerala.
Okay.
As Jasim said, this is not included in our degree syllabus. So I'm very weak in this topic, quotient groups and all. So I got a lot of ideas from your lecture. Thank you so much, sir.
Yeah. Hi.
I'm Sebat from Farooq College, Kozhikode, Kerala. Third year student, BSc Maths.
Okay. Which college?
Farooq College, Kozhikode.
Okay. Okay. Yeah.
As others said, this topic was not much familiar for me too. So the class was really helpful and the problems were really useful. Thank you, sir.
Yeah. Thank you.
Sir, myself, Shubham Jaiswal. I am from UP Kisan Postgraduate College. Thank you very much for this wonderful session, and it was the first time I saw the homomorphism with the general linear
Groups. Yeah.
group, and I only at this time I only know the normal subgroup or general linear group is SL and R, but from today's class I also learn some other normal
Yeah.
subgroup
So if
like
you if you take this diagonal matrices, okay,
G. Yes.
not diagonal matrices, scalar matrices, set of all matrices of the form lambda I, that will be a
Hmm.
normal subgroup. And so, and if you take any subgroup of R star, R minus 0, and
Hmm.
you put that subgroup, multiply that subgroup with the identity matrix, then again you will get normal subgroups. That is how you can construct normal subgroups of GL2R.
Hmm.
Okay.
Okay, sir. Okay, sir.
Yeah, I think they're called congruent subgroups. Yeah.
Yes, sir.
Thank you, Shubham Jaiswal.
Sure.
Yeah, some Hariharan Ramaswamy is asking that he is a new in competitive exams like NET. and how to approach sir as he is a beginner.
So the thing is that first you take some standard books on the subject and do all the exercises. That is the first thing you have to do. Learn proper, like properly you learn the theory first, then you do the problems in the exercise of that book. Whatever be the if for real analysis you do from Tom Apostel or Rudin, both are fine. And for algebra you can take this Einstein by topics in algebra. Then you do some previous year question papers. Then you will get some more ideas. That's it. So
First of all, make the concepts clear and strong, and then
yeah.
go for things.
Yeah, then you do the exercises. You do every exercise. Maybe some things will be very simple and few things will be very difficult. But to all the problems. Take your time and do it. Like.
Is there anyone
So
else
what
to
else,
ask?
sir?
Okay, I think there are. Okay, there's no other one. No questions. So I think
Okay.
we can wind up here. So
Okay.
thanks. Once I would like to thank all the participants for being with us, and also I would like to express my sincere gratitude to Arun for joining with us and helping in all these activities by providing many resource persons, contacts of many resource persons. I am very grateful to you, and hope that you will be with these activities
Yeah,
in
sure.
future too.
Yeah, I can sure. Yeah. Thank you, sir. Thank you for the opportunity. Yeah.
Okay, thank you.
Okay.
Thank you. Let
Thank
us
you.
wind up.
Bye.
Thank you.
Yeah, sure. Contact you.